Here's the top view again. Our magnetic field this way. It starts to rotate, right? We start out with this orientation. It starts to rotate. So what direction is the force on this length of the wire that's coming perpendicular to the page here with the current coming towards us? I is coming towards us out of the page. B is that way. So the force is straight up towards the top of the page. And over here the force is straight down. And at some instant later, what direction are the forces? And what's the torque now? 0. You can see that the torque, right, it's maximum here because the force is perpendicular. And then as the thing rotates, the torque becomes less. And it goes to 0 here. And if we had if we got it rotating, we started it here, and it started rotating. When it got to this point, it would have some rotational inertia. It would want to keep going. So as it went past this point, what would happen is the torque would be in the other direction. It would slow it down, and then it would go back the other way. And it would oscillate back and forth like that. You see that? Because the torque on this side is always down, and on that side is always up. And so it gets it moving, but then it slows it down. And it gets it moving in the other direction, slows it down, like a pendulum almost, right? It would oscillate back and forth like that. So if we want to make this thing turn around and around and around, which we might want to do if you want to listen to a CD or run a motor of some kind, you might want this thing to keep going around and around, not just oscillating back and forth. We have to do something so that when the loop of wire crosses this point, the current switches direction. If the current switches direction, then this force will switch to being up as this crosses over, and this force will switch to down, and that will cause it to keep going in that direction. And when it gets to this point, it has to switch again. And so every half cycle, the current has to switch to keep it with the torque always going in the same direction, causing it to rotate in the same direction. We'll talk about that in a minute. But first, let's finish torque. So that was the maximum torque I just wrote down. But in general, we can throw a sine theta in there. And what is theta? Let me write it here. This is the loop of wire is a plane, right? Defines a plane. How do we define a plane with a vector? We use the normal to the vector. So in this case, our normal would be pointing this way. Or maybe I should make it an area vector. I'll just leave it as an n. Normal to the surface. In this case, it points this way. the normal to the surface. And so what would theta be? Theta would be this angle right here, right? And in this case, the normal to the surface is here, and theta is 0. So I just mentioned that one application here is a motor. We could take a loop of wire sitting in a magnetic field, run a current through it, and what happens? We have a loop of wire sitting in a magnetic field, we run a current through it, it feels a torque, it starts to rotate. If we're careful by the way we control the current, if we keep flipping the poles so that the current is always in the same direction, then it keeps going, right? That's a motor. That's how we make turn electrical energy into mechanical energy. We put in electrical energy, flow a current, and we get a torque. The thing rotates. We get mechanical energy out. Right, a motor. And sometimes, right, your motor needs to be strong enough to turn whatever it is it's turning. Right, it needs to provide some torque to do its job. One loop of wire rotating may not provide much torque. But what can we do? We can run that wire around a whole bunch of times, make a coil. If we have 10 loops of wire here, and we run the current through and it goes around all 10 loops of wire, we have multiplied the torque by 10. So in general, we could throw an n over here, where that's the number of turns or loops. Okay, so that's a trick we use with motors and things to try to maximize what we want out of the motor. Okay, I wanted to show you something real quickly here. I told you that current carrying wires, no I didn't, I'm going to tell you right now. Current carrying wires produce magnetic fields. Okay? So what I've got here is a coil of wire and another coil of wire, and they're connected together, and I'm going to run a current through them. It's going to go through one and then through the other and back to my power supply. And I've got here a magnet, right, a compass needle. So I'll put that in here. And right now it's trying to align itself with the strongest magnetic field it feels, which is probably the Earth's field. It's having some trouble finding that. So it's trying to align itself with the Earth's field. But if I turn on my current, it will align itself with the strongest magnetic field that it feels, which is now caused by this current running through here. And if I turn it off, it goes back searching for the next strongest magnetic field to align itself with. Okay, so there it is. If I displace it a little bit, it tries to go back to where it was. If I displace it all the way around to here, it aligns itself with the field over there. It wants to align itself this way. So if I have it a little bit on this side, oops, just a little bit, it will go that way. So you can see that you turn on and off the current, and that compass needle is definitely affected by it, right? And that's how it was discovered. This was discovered by accident A strong current was being run in a wire on a lab bench. Oersted discovered this. He happened to have a compass needle sitting on his lab bench, and every time he turned the current on and off, the compass needle would rotate. So a current-carrying wire produces a magnetic field. Okay, we saw that here. So let's talk about that a little bit.